So, hello everybody. Now, I have actually uploaded one video before this lesson today, namely week 2, the p-type controller. If you didn't check it out, please check it out. It's quite important. And these two lectures are actually entangled. They are really important and coupled. We will be asking the question of poles and zeros and what happens if we have several poles in a certain region. We will be trying to answer that, and we will use the symbolic toolbox and the control system toolbox in order to try to answer this. Now let's start very basic. We have a first order transfer function. It looks like this. And what we're interested in is the following. We will look for the impulse and step responses, and we are changing basically the omega n parameter here between 0.5 and 2. We will be changing it in this interval, and we'll try to see what really happens. We might have done it already, but it will kind of add up. So let's start with that. So let's call it run1.m, clear TLC, and then so our transfer function actually looks like this, s plus omega n. So yeah, there are several ways of doing this. We can stick with the control system toolbox. We can just skip this notation and just say, okay, we will have omega n and then 1 omega n. And if we change omega n in a for loop like this, for I1 up to length omega n vec. And of course, omega n will be then one of the elements of the vector. So we can define this transfer function. Therefore, we will need omega n vec, which starts at, what was it again? 0.5 and 2. So 0.5 with 0.5 step size up to 2. For example. So this is one way of doing it, and this is the quickest way. We could also use the symbolic toolbox, sims s, and then maybe also sims omega n. It is a real parameter. And again, we would need a omega n vector here, like this. But of course, instead of defining it like this, most probably we will use this definition here. So it's quite possible to use both of these. But if you use this, what you have to do is basically you have to use substitute GSS, and then instead of omega n, the parameter, I want to plug in omega n vec I, and this will give me a transfer function, let's say GSS2. So this could really stay here, up here. So we take in omega n vec value, so omega n, and then we substitute it into this. But at this point, this is not a transfer function that we can use, actually. But what we can do is, if we don't, for example, want to convert it into a transfer function object at all, what we can do is we can just look for the inverse Laplace transform and say GSS2 divided by S, comma, ST, and we would have YT. So since we are trying to look for the step response and impulse response of this, we can use the inverse Laplace transform. And the reason why we divide it by S is that the output in the Laplace domain is GSS times US. And if we are using a step type input, UT equals step, then if you take the Laplace transform of this, basically the whole entire thing, what you get is US is equal to 1 divided by S. Since the output is transfer function times the input in the Laplace domain, we just have to divide it by S and take the inverse Laplace transform. We're not already done yet. We need to define a certain t vector, a time vector, because we will be generating the step response or impulse response. So let's give it a sample time. Let's say 10 seconds could be enough. So I'm just going to comment this out for a moment. And again, YT would be the Laplace, the time domain representation of the response itself. So let me just show it to you. Run 1. we should see several outputs here. Of course, we didn't define the symbolic t. There we go. We can see that the inverse Laplace transform also doesn't actually change. So this means that we could just do something like this, because it doesn't make sense to change because it's the same transfer function. The only thing that does change is basically the omega n value that we will put in. So we could do this. We could just define the transfer function. Substitute omega n vec is not really necessary at this point because we're taking basically the inverse Laplace transform of this. So instead of substituting into that, we could just say, okay, I'm going to substitute omega n in here. So this is basically it. So of course, there's a problem here. You can see what the problem is. We have the symbolic omega n, but we also have the value omega n. So what we will do is omega n, we will call it omega n val, and substitute omega n val instead of omega n, and see what the result is going to be. So you can see that it is possible to use the inverse Laplace transform. It will give us the mathematical representation. And as you plug in different omega n values, you see it changes. Now, the only thing left here is to just plug in t as a certain time vector, and then see what the response looks like. So what we can do is, of course, we can just define a figure. And then maybe hold on, and grid on. And then we can just also substitute, let's use another substitute because why not? So let's substitute t and t vec, and that's basically it. Now you can see that the subs function here is able to handle arrays. But did you catch the idea why I did have to use double subs function here? Because if I want to pass it as an array, I have to do it like this. But as far as I know, this would cause an error because I cannot put them into a single vector here. So let's try it. But I would say it should crash. But if it doesn't, it will be interesting. Oh, it doesn't. Interesting. Does it work? Not quite sure. Yeah. What do we get? Let's see. Yeah. It's not quite what we want because I'm substituting. Oh, tvec, of course. Let's see. There we go. Yeah. Okay. It doesn't work because you cannot stack omega n val, which is a scalar, and tvec as a vector. So what you can do is you can either use another for loop and then do it tvec I or j or whatever you will call that, or just separate them and substitute vectors on its own and scalars like this. So if I convert it into this, now it should work. Of course, I can call it y at this point and say plot tvec, comma, let's call it yvec for consistency. So let's run it. There we go. Of course, we might want to add some line width. There we go. Now, this is one way of accomplishing this. This is the symbolic toolbox version. It is quite generic, so you can just go ahead and use it for different kinds of things. But since we have an expression and we want to just use that expression with its values, this doesn't really have to be the choice that we will do. So I'm going for the simpler version here. Actually, yeah. I can also show you something neat, by the way. Sometimes it becomes handy. Since we have yt here, and since it's depending on t and omega n, What you can do is you can do the following. Let's call it fyt as a function and call the MATLAB function here. And then give it the expression. And it will create you the function. Then you don't really have to use the subs method here. Since you have already the function, it takes two parameters. One of them is time, and the other one is omega n. And as you can see, there's a element-wise operator here, which means that you can safely pass some vector in it, and you will get the result. So let's try this. This is also sometimes a lifesaver. So let's convert it into a function. At this point, well, we can just skip these and say fyt tvec comma omega n val should give me what I want. So let's call it yvec. And let's close all, let's clear and run it. And there you have it. It's just the same. And we have a function and yvec has the values. You don't really have to even care about converting into double because the MATLAB function itself just creates a MATLAB compatible function. So it cannot really return symbolic expressions. It has to return double as data types. So this is one way of doing it. And well, yeah, if you don't really want to mess with any symbolic toolbox stuff, what you can do is you can just skip everything here. We don't really have to use that. Not even this one. Maybe the time vector can stay. And let's go ahead and use this. Because it's shorter, it's making more sense. So we have a certain time vector, we have to find that. Omega t, maybe yvec, depends. And then step, and then gs. You can also provide your own time vector. And then you just plot tvec comma yvec. The line width. There we go. Now, you can see it works pretty much and it's the same. So yeah, I wanted to show you the different ways of doing it. So we actually did talk about this as far as I remember. If you just use TF and then just add a S here, an S term here, you're just multiplying with S, which should take the derivative of the input and output, so you can get the impulse response like this. Or you can do it in the symbolic toolbox version where you just don't divide it by S and take the inverse Laplace transform of the actual transfer function to get to the impulse response. And you can see it is kind of compatible with the step response. We most of the time don't really use this because impulse response is important, but in terms of control system design, we are not leaving any system alone. We're just applying a constant. At least we're changing the input as constant jumps or constants. So it's quite important to look at the impulse response, but we focus on the step response. Yeah, so let's get rid of that. I'm going to skip that part. What I really want to do is I want to have a small subplot here. I want to compare it to something, one row, two columns, and the first one of that should be this one here. Let's give it also some labels. The x-axis is the time vector. The y-axis is basically yt, the step response. The title should also be step response. That's it. Now let's create also another one, which will be the second one here, all on grid on. But here we will have the real and imaginary values. And as you can imagine, it is the S domain. And let's look at the poles. So you can see that I want to create my figures and subplots on top of my file at the first lines, maybe. So, and I want to use a for loop, and then I want to decide which plot goes on which subplot or figure. In order to do that, I use most of the time the axis handle here, get the current axis, GCA, so it'll be assigned to AX1. So this is AX2, get the current one, because if you call subplot, it will generate a new one, and that is one, the current one and that becomes assigned to the variable here. So if I specify that, and if I say, okay, this will go on AX1, it will automatically plot on that one. And yeah, I know the position of the pole because we just have one pole. It is exactly at minus omega n. So I'm just going to plot it there. So yeah, nothing fancy. So therefore, I have to specify this goes on the second plot, and that's also basically it. There we go. We can see some stuff, probably, maybe not all of it is that obvious. So what I really want to do is now I want to have a certain color, and I'll change its brightness or tone in order to just match these data, this visual data, to certain change. So I know that omega n will be increased if, for example, the color gets brighter. If I have this as a setup, I can then match which one of these step plots and these pole plots here are assigned to which omega n value, basically. And I can do that by specifying a certain color or color brightness. And you can define the color with as a RGB vector. So the first one corresponds to red, second one to green, and the third one to blue. So it's a 1/3 vector, basically. But the value should be between 0 and 1. Therefore, we can just say, okay, if I want to have everything in red, I can just say 1, 0, 0, define this color, and then just say, okay, the color should be color. You don't really have to do this way. You can just skip this part and provide it here. But yeah, I like to specify that the color is the color. It will make everything red. So it's not what I really want here. But I can change its brightness based on this value here. It's between 0 and 1. And here I have an increasing variable, I, which starts at 1 and stops at whatever the length is. If I normalize it, if I divide everything by the length of this, I'll get a number between 0 and 1. So that's going to be my strategy. I'm just going to say, okay, I divided by this length. If I is equal to 1, it'll be 1 divided by 3, let's say. And if I is 2, it's going to be 2 divided by 3. And if it's the last one, 3 divided by 3 will give you 1. So you will have 0, 0.33, 0.666, and then approximately 1. So this will be a dark color, brighter color, and the brightest color. So you'll get that effect that I'm talking about here. So you'll see, there we go. Now, of course, in terms of the poles, it's not really that obvious. Yeah, but other than that, we can see, of course, if it's a dark color, it is a lower omega n value. So if it's the lower one, this one is basically the dark one here. If it's going to the left, it is going to be, it is approximately going to be this brighter step response here. And what I can conclude from this plot on its own is that if the magnitude of omega n increases, if it's becoming far away from the origin, as you can see, 0 is the origin here, we can also maybe plot the origin here. So by the way, if you call xlim and ax1, as far as I remember, you will get basically the limits of ax1. So it's 0 and 10. And if I do it for ax2, I get minus 2.5, minus 0.5. And I can change it by just saying, okay, just update it with my new vector here. The limits should be maybe -3 to 0 here. I can do that and it'll take effect, hopefully. Why didn't it change? Interesting. It should be AX2. I'm sorry. It did affect this, the left one. It's AX2. So there we go. Now we have more room and space, and we can see what is really going on. Yeah, here we have the origin. We have the j omega axis here. We can plot them too. We can just make something like this, maybe 0.2, and then just plot another line on ax2. And let's say, for the y-axis, we have to specify 0 and 0 as the x values, and this will come directly from the y-lim here. And let's assume that this is the line. And we can also plot the, here this will be the x limit of x2, and we will just have 0 and 0, of course. So this should plot us a grid there, you can see. And you can also do something like this if you want to be real fancy, ax2 and then 0, 0, and then have maybe a point there that shows us the origin. And there we go. Now we have the origin here. And we see that this is minus 0.5, minus 1, etc., etc. We also can change the type of the grid because this grid doesn't really make sense on the S domain. Instead of having this grid, we can just call the S-grid method. It requires some zeta values, which we can just give as 0.5 maybe to have the generic one, or maybe equal to 1. And then some omega n values, which I'm going to directly provide from omega n back here. There we go. Now we have also these omega n plots, which are basically going through these here. Now, this is basically the maximum I can draw about a first order system. If the pole starts at here and goes here, the step response is as shown here. And all I can say is that in terms of settling time, for example, or rise time, I can say that the rise time increases, the settling time increases if it's getting closer to the origin. So it slows down. That's the important thing that we should maybe have here. By the way, MATLAB has some symbol support here. I did wrote down RE and IM, but what I can do is I can just say, okay, I just want to show the sigma here, and then maybe J omega. And as far as I remember, it should take effect. We see J omega there. You can see sigma. If you want to be real fancy, you can also do this. So that's all about the visual plotting stuff that I'm going to get in detail for today. So that's it. For a first order system, we've learned that increasing omega n means faster settling time responses. So that's basically it. It doesn't overshoot because it's a first order system. That's not the case for second order transfer functions, of course. What we'll do is we'll just create this transfer function here, look for certain intervals and see what does affect what. So we'll hopefully get a deeper view of a certain second order transfer function. The second order transfer functions are really important. You have to be knowledgeable about them, because most of our control system design course relies on the second order transfer function. This is kind of the ideal that we're after. So therefore, you have to know these. So let's go ahead and do it for a second order transfer function. Let me create another run file here. There we go. Now, the first one is omega n equals 1. So we will have a certain omega n value here. It will be equal to 1. And then the zeta here is in a certain interval, namely 0 and 1 and 1 and 2. So let's have 0, 0.5, and 1. And we will have another one which starts at 1, stops at 2. So therefore, we will not have basically a plot that relies on omega n values. It rather relies on the zeta values. So therefore, all that was about omega n vec will become zeta vec. So it's kind of the same, but a little bit different. So we will do these steps too. And that's basically it for here. Of course, we have zeta vec, so why not use it? So zeta vec, we also have omega n. Maybe we should call it omega n val. Omega n val. There we go. So for omega n. So zeta, now our second order transfer function looks like this: 1, 2 times zeta times omega n, and then omega n squared. So let's have t vec. So we're looking for the step response. We take the color, we plot it, and of course, in this case, this is not really the pole. So we can actually use the transfer function itself in order to draw the poles, or we can do the following. We know already the poles of a second order transfer function. First of all, we know the real part of it. It's going to be zeta times omega n, but negative. So it's minus zeta times omega n. And the imaginary value will be square root of 1 minus zeta squared square root times omega n. So this is basically the sigma part of it. This is the damped frequency equation. But it's basically also the solution of this polynomial here. We can directly calculate it using roots function here. So I'm going to place these. They will have some color assigned to it. Let's get rid of this, this, and this. Actually, these may stay. And I'm not really interested in the limits for now. Maybe I should leave it there. And the origin is not really important, so let's get rid of that. And that should basically do the job here. Let's see if it works for starters. Omega n vec is not specified because of this color thing here. It should be zeta vec. Yeah, it's kind of a progress bar calculation here. If you want to show the percentage, this is also basically the percentage that's done. So we use it as a color to indicate some movement here. So there we go. Now we have this interesting thing here. Yeah, maybe I should give different omega n values. Omega n is that. Just give 1 up to 3 maybe. And I can see that it works, so I should maybe increase the step size here. So I'm just using 3 different values. Maybe increasing that will help us visualize it. And there we go. We have this neat result here. Yeah, actually, what we can do is we can change the y limit of this plot of the second one here. So the y limit is more important. Make it -2 and 2. Yeah, that's basically it. Now let's also, by the way, copy it and then paste it here. Take this zeta vec and plug it in here. Figure 2, basically the same. We'll see the effect. Yeah, this one should actually wait a little because it's not entirely correct. We'll be talking about that. So here we can see basically that this is the j omega axis here. And still, I'm not happy about it. It is still between here. Why is it not working? Let's see. Oh, it's still x limit. That's why. Okay. There we go. Now we have a better view. if it's the dark color, then we are basically starting with zeta equals 0 here, of course. And if we have zeta equals 0, we are on the j omega axis, by the way, obviously. And these are actually pole pairs, but I did not plot the conjugate here. Let me do that too. So the other one would be this here. Since I plotted it manually, I also need to have the conjugates. Now, if we have this dark color here, we can see that we are on the j omega axis and zeta is equal to 0, which corresponds to no damping at all. So 0 damping, because zeta is the damping ratio. And omega n is basically equal to 1, and we are on a circle. That's the natural frequency. And it's basically a positive number, and it's somehow related to the speed of a thing, of a signal, for example. And therefore, we call it frequency. If you increase the frequency, you'll see that it will speed up and there will be more cycles in terms of sinusoidals. So if we have zeta equals 0, we are on the j omega axis. If we increase zeta to the value of 0.1, we are slightly on the left. It has a very high imaginary value and very low real value here. And as zeta increases, we are basically on the circle moving towards here. And you can see that since it's the cosine value, the cosine of this angle gives us the zeta value here. You can see as the angle decreases, cosine of a lesser angle gives you a higher value, so zeta increases. So at this point, zeta is exactly equal to 1, and we are on the real axis. We have no imaginary part, and we're at this point where the poles coincide. So there are 2 minus 1 poles on top of each other at this point. So if zeta is equal to 1, it's critically damped. If zeta is equal to 0, it's not damped. And between not damped and critically damped, we have underdamped, which means that the oscillations on the left do not vanish. They don't go away. They're there. But as zeta increases, the peak values here decrease. At a certain point, it's almost no overshoot at all, no oscillation at all. So it means that if you have a certain second order transfer function, if it has complex conjugate poles, the imaginary part actually decides on the oscillations and overshoot characteristics of a system. Therefore, if we have a first order system, we don't have complex values, so we don't have oscillations whatsoever. So if the zeta value increases, overshoot decreases. We have a relation between them. We have a formula between zeta and overshoot. You can have a certain zeta value, end up with a certain overshoot value. You can calculate that, or you can also do the inverse where you have the overshoot, the amount of overshoot, and you can just calculate back what zeta is. So it means that if we will design certain controllers with an overshoot requirement, we can directly conclude zeta. We can come up with a certain zeta value. Given overshoot, calculate zeta, it's possible. But we also need to take into account that different omega n values can end up in the same overshoot. It means that it's not uniquely defining a system, it defines a family of systems. Namely, if you have a certain zeta value, you will be on this zeta line here. And with the same cosine value, you can just come up with infinite amount of solutions. So zeta is not unique in this sense. You need another definition value, something about the system, in order to conclude a unique second order system out of that data. So zeta is on one side. We have zeta. We looked at omega n, but omega n is fixed for this graphic here. And for the second part where zeta is actually varying in a different interval between 1 and 2, if you look closer, you'll see what my problem is, what my fault was actually. Let me copy this one down here. So the problem here is that zeta is greater than 1 in this case, and 1 minus a greater value than 1 gives us negative, and this becomes complex, even though this should be a real value because I omit the I part or J part here. So therefore, I have to reverse the order instead of having 1 minus zeta squared, I should have zeta squared minus 1. But then this means that this is not going to be the imaginary part anymore. It's going to be added or subtracted from the real value because it's a real value. Based on my assumption, I have to take it here, placed here, because, well, it's not imaginary anymore. It should be a real value because the negativeness of this times the j value gives us j squared, which is -1. So we take it out and place it here. So yeah, this can stay 1 for this system as far as I am concerned. And yeah, it should be it, I guess. So now we have 2 plots. So let's just take this and this side by side, and there we go. Now, of course, on the right-hand side, we need a little bit more points. There we go. Now, still we are changing the zeta value, but the interval of zeta is greater than 1. At this point, we're talking about overdamped systems, and you can see why the name overdamped is actually used here. And 10 seconds of simulation time is also not really doing it for us here. So let me redefine it here with a higher value, for example, 30 seconds. And maybe I should also, this should be ylim, not xlim. There we go. Now we can see that there are no oscillations if zeta is greater than or equal to 1, because we started with 1 and increased it. And yeah, there's no overshoot here. It's called overdamped. And the reason why we call it overdamped is due to the fact that we have the critical damped solution here, which is the first one, the darkest color here. And if we keep increasing the zeta value, this system slows down. The whole step response slows down. This is not really necessary in this case because we can have zeta equals 1, and it will give us the settling time value, or approximately the value, because it's not really our settling time formula, which we will see, or which we had in the last lesson. It's not applicable to zeta greater than or equal to 1. It's between 0 and 1, 1 not included, 0 not included also. So therefore, our settling time formula, which we have, is based on underdamped systems. Here in this case, we have overdamped system. The system becomes unnecessarily slow as we increase zeta, whereas we can have a non-overshooting step response with zeta equals 1. And we can also see what the reason behind that is, why it slows down. Because if we take a closer look to this, plot here, we can see that the omega n plots here, which were the circles, omega n circles, we only hit it with zeta equals 1 and omega n equals 1. As we increase zeta, none of them coincide with the omega n circles here, because it loses its meaning. The omega n circles do not define overdamped systems at all, only for critical damped and underdamped systems. You can use omega n only for underdamped and critical damped systems, not for overdamped systems, because we have a center point, which is the critical damped solution, and the part that I added and subtracted to the real value here, this exact point part here determines the distance from this point, because you're adding or subtracting it. So the midpoint is minus zeta omega n here. And as zeta increases, the square root of that number will give us a certain value. For example, if zeta is equal to 2, we will have square root 3 of that, and we will have minus 2 here, 2 plus square root of 3 and 2 minus square root of 3 will be the position of the poles. And one of them will be further away because we are subtracting a certain value, And we know that this part is positive, so it will give us an amount here. And that amount will then be subtracted from this, which means that this will be far, far on the left, whereas we're adding actually a certain value to the real part of our pole, which means that this one will tend to the origin, and it could be possible at some point to hit the origin or even pass through the origin. And that can happen if I increase this, for example, let's say 4. It's a bit too much, but let's see. At some point, we would also have, we're just getting closer and closer. It seems like we need a little bit more than that. But you can see there's this part here is crowded, whereas this part here is far, far away. And again, we don't hit any omega n value or omega n circle here, except zeta equals 1 here. So we don't work with overdamped systems that much. And the reason behind that is you can see it becomes slower and slower and slower. As zeta increases, it becomes so slow, it's unnecessary. If you have a kettle at your home, if you want to just boil water, you just hit your kettle and it'll heat up, but it will heat up so slow that you will just skip it and just maybe look for another option. So in real world applications, most of the time overdamped systems are not really that interesting for us because it takes too much time if we increase zeta. And the reason behind that is we can have just a basic reasoning here. And the reasoning is the following. One of the poles is too far on the left. Let's come up with a pole, let's say s plus 20, whereas the other one is s plus 2.2, something like this. This multiplication will give you a zeta value greater than 1, for sure. You can go ahead and check it out. Now, this is the characteristic polynomial. So let's have that. And let's say we just have 4 as the value because 20 times 0.2 is 4. If you apply 1 to it, it will have the DC gain of 1. So if you apply a step to it, it will track that step. Now, since these are real poles, what I can do is I can come up with 2 different systems. And then let's also have 0.2 and s plus 0.2. So this would be the same if I had a cascade connection here. It would be basically the same. You know, the reduction technique, you can just multiply them, it's going to be the same. Now think about this as a high-speed internet connection. This part is the model of the internet, of the web, and this is your phone. Now, if you have a fast connection and a slow phone, your internet connection will be slow. If you reverse the order, if you have, for example, a slow internet connection, so let me change the connection here. If we have a slow internet connection, but a very fast phone, it doesn't matter, the overall speed will be decided based on the slow part, which means in this case, it's your phone, in this case, it's the internet. But your overall connection speed is determined by the overall system. Even if this one here is very fast, this one, you have to wait on this one because it's slow. And that's basically it. You can also think of a car engine and all the dynamics behind that. And yeah, your car will be slow. If just one part of your system is slow enough, then it will kind of decide on the speed. So the slow one decides on the speed. That's the important thing to know here. This may seem a problematic thing, but if you use it well, it's not. So there's kind of this trade-off here. If you are wise enough, you can use this for control system design, but sometimes if you design overdamped systems, this might not be the case that you're interested in. Now, yeah, therefore, I can safely see that, yeah, it becomes slower and slower. Here I had both poles on top of each other at this exact point. But if zeta increases just a little bit, I get immediately this pole here, which is closer than this one here, which means the closer you get to the origin, the slower it becomes. So therefore, we are not really interested in overdamped systems. That's all what I'm going to say here. It makes sense to have a certain overshoot and a certain settling time, a reasonable settling time value, and that would be your ideal system behavior, because for most applications, it's not possible to have zero overshoot. You will have overshoot for some reason. But a slight overshoot or an overshoot value close to zero is sometimes ideal, and sometimes it's not. It depends on the application. But we will be looking for certain settling times and a range of maybe overshoot values, and that will be it. We are, of course, not interested in these high oscillation responses here, but also this overdamped one is also not really useful for us. So knowing your second order system is important. You should look at the zeta value and see if you're kind of at a good spot. If you have done anything wrong, you can just check it out by controlling your zeta value and your responses. They should align. If it's not, there could be another explanation or a problem. So that's basically also this task here. We did look at that. Now we did change the zeta values. It changed the overshoot characteristics. What about changing omega n and fixing zeta values? Let's see what that will give us. So let me just comment this out, copy this. There we go. Now I can get rid of this here and change it later. So now in this case, we have omega n equals, what is it? 0.5 to 4, 0.5 to 4. Now this will be omega n vec, and then we will have a zeta value here. Again, I have to change everything accordingly. So we're looking for a certain omega n value from the omega n vec, and then we will use omega n and zeta as usual. Look for the step response. In this case, my looping vector is omega n vec, so therefore I have to change that. I will have the poles. It is going to be a good zeta value, so I can conclude this one here. Plot that, plot that. Maybe omega n vec is a better choice here, but the zeta value should be zeta itself. And I guess this one is not necessary. Let's see. Now, since this is basically zeta equals 1, it means that we have two poles on top of each other for each omega n value. That would translate into the following. For example, if we have 0.5, we have 0.5 divided by s plus 0.5. And it's connected to basically it's connected like this. So it's basically the same system twice connected in series, and that's it. And that would individually mean that they will have a certain speed here. And yeah, if you have a certain speed for your internet and approximately the same speed for your phone, you will have basically a system that has a certain speed. That's it. No one is dominant in this case, so we cannot decide on the slower or faster one. They are at the same speed. And as it was the case for first order systems, if you increase omega n, as you can see, the system just speeds up. It becomes faster. So if we want to have a fast step response, we want to be far away from the j omega axis. if you want to have a certain overshoot, then you will be on a certain line with a certain angle, which cosine will determine basically the zeta value and therefore the overshoot value. Now, what happens if we change it? Let's say, let's have 0.5, a different value. It should have overshoot now. But you can see that it is on a zeta line, on the zeta equals 0.5 line. They have all these systems have the same angle, as you can see here, but their omega n value changes. So we are hitting a different orbit, sort of. But the nice thing about this is that the peak values here are aligned. All the peak values are at the same level, which means that all these step responses have the same overshoot. Changing the natural frequency in this case makes sense because the natural frequency will decide on its speed. The frequency decides on the speed, whereas zeta value already decided on its overshoot. So pick a certain zeta value for a certain overshoot, and then change your omega n as it suits you for a certain, for example, setting time value or rise time value. So that's kind of the strategy in choosing the zeta and omega n values, because these then will determine on your poles. And for the p-type controller design lesson that I've already uploaded, you will then decide that zeta and omega n will form the second order transfer function, this ideal transfer function, which looks like this. These should be the slowest poles of your overall system in the closed loop. Why? Because we've talked about overdamped systems, and we had this sort of behavior here, whereas the slow ones were closer and closer. And we said that if this pole and this pole, if you have 20 and 0.2, then the slower one will decide its behavior. Here, we are looking for the same. Our two poles as a complex conjugate pair should be as close as possible to the j omega axis compared to the remaining poles, or even zeros maybe. I will come back to this idea, which is called dominant pole placement, because the dominant poles are the slower ones, and everything else should be faster than that, then the slowest one is deciding basically its behavior. And of course, you can repeat it for different values, for different zeta values. Since you have the code, you can see what is going to be the result here. But as you can already maybe guess, is that they will have the same overshoot, but increasing omega n will speed it up, decreasing it will slow it down. And that's basically it. Now, we are going to pick a certain second order transfer function, GS, which looks like this here, but we will add a third pole, and we will see what is going to be the result of certain p-values. So let's do that. Yeah, I might just pick this here. There we go. Now we know what the zeta value is going to be. Let me see what it is. 0.5 and 0.5, so just leave it there. And again, is also 0.5. But now we have pvec. We are adding a third pole here. And I don't know what the values were. Let's see. 2, 10, and 0.1, 0.5. So 0.1, 0.5. Yeah, and 210. Okay. There we go. Now it should be pvec. I'm taking p values here from pvec, and the transfer function will be this times p divided by s plus p. Now the reason why we are picking basically p divided by s plus p is to not change the gain of the system. It's steady state gain. I don't want to touch it. It should be the same. And if we plug in s equals 0 from the final value theorem, you'll see that G0 times P divided by P is going to be G0 itself. So it will have the same DC gain as it had already. So let's basically change the p-value here, look for the step response. In this case, we will have pvec. I'm still going with this coloring theme here. Have the color, look for the poles. Yeah, at this point, I cannot now use this, or actually I can just plot the third one here. It should be minus p and 0. And that's basically it. Now, of course, I don't really have to plot it over and over again, because these are not changing at all. So I can just place them here, maybe assign them another color like black. Because we don't really have to plot them over and over again. You can also use PZMap or something like that in order to come up with this value, but I know that this is minus p because it's just s plus p equals 0. Now, and we are going to repeat it for the other p vector. So let's call it 2. Let's get rid of that. There we go. Yeah, I guess this should do the trick. Four. Of course, we did forget it somewhere here. So it's going to be omega n. Let's see. Now, first of all, we have added this one here. It seems like we need even more time than 10 seconds. But here we have another plot which seems like it's happy with its value. But it did slow down overall. Let's maybe increase this t vector here in order to see the whole picture here. And of course, I should maybe increase the grid here. This is maybe fine. Maybe even half of that. Or maybe this. There we go. Now, here, this is the third pole here. And these are basically the omega and zeta pair. This is basically the pair. And this is the third pole. If I add it at minus 0.1, and if it goes up to 0.5, this will be the step response. Now, I can see that we had a certain behavior where this one was basically slower and it decided on the overall speed of the system. Whereas if we increase the absolute value of the third pole, or if we are moving it to the left, we can see now the whole overshoot of the system does basically change. Its speed does also change, but its overshoot value is affected the most. And the rise times do not stay the same. The settling time does change. It did affect the system since it was dominant, and it then became, or it will become more and more not dominant. It will go to the left. And if it's becoming faster, then these slow pole pairs, or the pair here, will become more dominant, which is exactly the case on the second plot here. We can see that now the pole pair is closer to the j omega axis. We start at -2, and we'll see how we can flex it here. But we can see it starts here and goes to the left. And yeah, the overall shape of the response, the overshoot values, the settling time value, the rise time value, all the time domain characteristics are going to be close. They will, of course, they will be affected from third pole, but they will be close. So I can determine the overall setting time, overshoot, peak time, rise time, whatever the time domain characteristics are going to be. I can determine them based on only zeta and omega n by just disregarding p. And this is nice because how many p's, how many poles you have added to the system, it doesn't really matter. You can add 50 poles if they're not in the dominant region. The so-called dominant region is basically this region here. If they are not in this region, then these are the slowest poles, and they will decide on the overall characteristics of the system. The overall behavior depends upon these two poles. Therefore, this zeta and this omega n value exactly. And it's quite nice. If you have a 8th order system, you can just decide on 2 poles, assign them somewhere in the dominant region, and push 6 poles out of the dominant region. If that's possible, then you can use this setting time and overshoot formula, or all the knowledge about zeta and omega n and second order systems are applicable to this system. If not, it will fail miserably because, yeah, it doesn't really represent this system at all, because it should not also represent this system. It's not a third order system. We are using a second order system in order to guess the behavior of a third order system. This doesn't really make sense if one of the poles, if it's a third order one, if it's not far away from the 2 poles that we have here. So this raises another question. If that's possible, what about zeros? So what I'm just going to change the way that it affects the transfer function. You can just change the notation too, but I'm not going to bother with that. I'm just changing the transfer function definition. Nothing at all. Only these 2 lines. There we go. Again, same scenario. If the 0 is far away, I have added a 0 instead of a pole. I took the inverse of p divided by s plus p, which makes s plus p times or divided by p will be added to the system. Therefore, we have a pole pair, and these are basically zeros, not poles. And we can again see that even if it's a 0, if it's far away, it will not affect the system transient behavior. We will not see the effect. We can use the formulas for this. Even if it's a third order system, I can go ahead and use the second order formulas. But if the 0 enters the dominant domain, then we have a slight issue here where we would have really high overshoot values. You can see that it surpasses 300% overshoot, because if it's hitting, 200%, it's almost 300%, because the value is 1, it hits almost 3.2, something like that. So 220% overshoot is crazy, and only possible with a 0, of course. Because if you add poles, more poles, all you get is a sinusoidal out of it. But in terms of a 0, it's not really the case here. And you can see that these formulas for zeta and omega n will not decide on the behavior of this system. If we are designing a controller or a closed loop that looks like this, then we are in trouble. It will not work like we want it to work. But if we are able to somehow get rid of these poles in the dominant region and the zeros, if we can push them far away, then we're good to go. We can just go ahead and use the knowledge that we have. It is important to note that a 0 in the dominant region is far worse than having a pole in the dominant region, and keep that in mind. By the way, most of the time during the controller design, we ourselves are adding the 0. That's another issue that we should face. So the 0, if it's not present in the system, then it's highly probable that you have already added it with your controller and the structure of your controller. So we have to be careful about that. But other than that, if we are trying to use the dominant pole placement, which is basically going to be going on for weeks in our course, then you have to keep the poles away from the dominant poles or the zeros. Yeah. Let's see, what else do we have? Now there's also an additional task, F and G. You can go ahead and try that. I will just talk about that. Now I've talked about overshoot, but you will see overshoot probably next week. I don't remember, but you can look up the formula, or I can show you the formula. It's just a very basic formula. But we have two basic definitions here. One of them is the settling time, which means that our system settles down to its 2% band. If it's not leaving that band, if it's wiggling in this 2% band of its steady state value, then we are basically done. And the first instance, the time at that instance, we call it the settling time. So basically after settling time, we don't really think that the system is in its transients. The transients are gone. We're in the steady state. So it's settled down. So that's the name. Rise time is basically based on two different definitions based on the order of the system. For first order systems, it's kind of like 100% increase in the response as far as I remember. I could be wrong. We should check out the textbooks. But for second order systems, it's the time that takes this, that starts with the 10% band and the 90% band. The amount of time it takes to go from 10% up to 90% is basically the rise time here for second order systems. And for the first order systems, as far as I remember, it was from 0% to 100%, something like that. So the amount of time that is needed for that is called the rise time. And in the case of boiling water, it makes sense to look for rise time, because the faster this is, the better it would be, actually, because we don't really care if our water is exactly 100 degrees Celsius or if it's just 95 or 90 even. It's not really that big of a deal, but we want to have boiling water as fast as possible, so rise time would be a good case for that. For settling time, I would say if you're hitting the gas pedal and if you have an economic car, then you're just happy that it gets to a certain velocity in a certain time window. Yeah, if you have a race car, again, you would go for rise time, etc., etc. Now, here I will quickly show you the code that is necessary to just use numerical tools to come up with a formula that looks like this. So we have a mathematical model where zeta and omega n is in the denominator here. We are looking for the coefficient that will represent this settling time behavior of a first order or even second order system. And yeah, we have talked about the fact that it takes the time constant times 4 or 5 based on your definition to settle down for a first order system. And the same almost goes for the second order system. So 4 divided by zeta omega n will be the response here. Whereas we can use a first order model, which has just zeta in it, or a second order model, which has zeta square in it, to model the rise time, and we will see what it is. So I will be uploading this PDF, and you will be accessing it. You can see there are different plots that we also have generated here today. And the dominant case, the non-dominant case, you can see it goes for the zeros, still there. And yeah, you can use the MATLAB's fit function, but you have to generate also the data set in order to use that fit function. So it starts here. The settling time, we have a region of, or basically all the possible values for zeta, all the possible values for omega n, or even a region. We are defining a 2D region on the S domain. We take points from there, look for the step info of them, generate the transfer function, look for the step info, and we are just making a table of data, which we will then feed to the fit function here. We say, okay, this is the parameter, this is another parameter, this is the coefficient. Just come up with a coefficient that fits this model, basically, and it will give us the result. The same goes for all the other examples. We just stack the values of zeta, omega n, settling time, rise time. And then we just create a model where we are looking for A, and we have data about X and Y and the outcome, of course. So it should come up with A. We can just copy and paste it, and you can see for a first order system, it's 3.9121. For a second order system, the fit function calculated 3.7972. So we take it roughly equal to 4, but in reality, as far as I remember, it should be, since this is numerical data and it doesn't have the mathematical proof here, it's 3.9118, something around that, but we will just take it 4. And then we can just do the same for the rise time, and you can also see that This is basically the rise time formula. Now, this is good for using it to come up with theta and omega n values, because in this case, you just pick a certain overshoot for zeta. Once you know zeta, you can just plug it in here. You will, if you know the rise time, you will come up with omega n, and bam, you have your system. And the same goes for here, but yeah, if you have the zeta value, you can just plug it in, no problem. But if you have two different formulas, like one for settling time and one for rise time, you have to work a little bit to get the exact zeta and omega n values that you are basically looking for. Now, hope that this lesson has taught you something. Maybe you should be more comfortable with second order systems. Hope that it did the job here. We looked at first order and second order systems. The most important thing that you should remember is that the slower one dominates the overall slowness, or even the overshoot. So slow behavior dominates the behavior, and we will be dealing with high order systems. But all that we will do is, in terms of transients, use the settling time, rise time, and even the overshoot formulas in order to come up with a second order system. And we will try to model a high order system as a second order system, which is called dominant pole placement. We will try to place the poles so that it will have the behavior that we are looking for. Now, in the upcoming weeks, we will be more considering the actual design. And if you didn't watch the previous lesson that I have uploaded, please go ahead and check it out. It's called Week 2 P-type controller. It will make more sense at this point. So if you have any questions, feel free to ask.